So yeah, my name's Dre Helms. I use they, them pronouns. I got my PhD at UC Berkeley in 2019, and I've been a postdoc at Lawrence Berkeley Lab since then. And I've been focused on developing these integrated load shifting systems as part of my postdoctoral work. So I'm going to kind of describe what I mean by all of those words, integrated load shifting systems. And yeah, it's a real pleasure to be here. So thanks for having me to kick off this retreat. So really kind of broadly thinking about decarbonization, there's so many different arenas where we can decarbonize our technologies. And so my focus in this presentation is on buildings, particular building energy. And even zooming in a little bit further, I'm focused on heating, ventilation, and air conditioning. So here that HVAC just stands for heating, ventilation, and air conditioning. So there are some real opportunities to integrate energy storage into HVAC design. So what we see actually kind of looking across the nation and in fact looking across the world is that energy for building, heating, ventilation, and air conditioning drives peak electric demand. And right now in the US, the building sector accounts for almost 40% of our US energy consumption. And of that 40%, about 50% of that is electricity for HVAC. And so as we think about decarbonizing our technologies, decarbonize our buildings, we're going to be electrifying these technologies. And that's actually going to lead to further stress on the electric grid. And so what we see in projections is that electrifying building heating, so going from gas-powered heating to electric heating via heat pumps, is likely to increase building electricity demand by 73%, which is pretty significant. And so one of the ways we can kind of mediate this and help prepare our society for an electrified grid is to shift heating and cooling loads. And so what I mean by shifting loads is kind of using storage. So we're all used to thinking about electrochemical storage like batteries, Tesla Powerwall. Sorry, is there a question? Okay, I think we're good. So we're all used to thinking about electric batteries, but here I'm going to be talking about thermal batteries. And so right now, US building operations count for 30% of our greenhouse gas emissions. And so the solution that I'm thinking about here is as we electrify these systems and as we add this energy storage, we can reduce the direct greenhouse gas emissions of our buildings by a pretty significant amount. So I mentioned, okay, storage technologies, but we're doing thermal storage rather than electrochemical storage. And the storage that I'm focused on uses solid to liquid phase change material. So you can think of phase change material. We interact with a lot of phase change materials in our lives. One key example is water. So you interact with water in several different phases. You interact with ice and liquid water and steam. And so phase change material you can kind of, think of as something like water, and hopefully it's a little bit, less intimidating. I always tell this to my students in my thermodynamics class. So anyway, the technology that we're working on encapsulates this phase change material in a heat exchanger. And so a heat exchanger is, kind of like these boxes that you see at the bottom right of this slide. It's essentially a fluid flow passage with another material on the other side of those passages to transfer heat to and from that material. And so the material that we're using in these active heat exchangers is a salt hydrate. And so it's kind of looks like this. What you see here is lithium nitrate trihydrate, salt hydrate. And this salt absorbs water into its lattice structure. And then when it's heated, it can release that water. So this is a purely physical process. This is not a chemical reaction. And what we see, kind of hearkening back to ice and water and this thing that we're familiar with, you can store a lot of energy in changing a substance's phase. And so we see with changing the phase of water from water to ice that we can store 334 kilojoules per kilogram, which if you compare to changing the temperature of water by, let's say, 1 degree Celsius, this is almost 100 times greater energy storage. And with these salt hydrate phase change materials that we're looking at, we see still a pretty high energy storage density. And so the benefit of using these salt hydrate phase change materials for this thermal storage is that we can control the temperature at which energy is stored. And so this is really beneficial because a lot of our end uses require energy at a certain temperature. And so getting into those end uses, requiring this energy at a certain temperature, that kind of brings us to heating and cooling systems. So the work that we've been doing at LBL is to develop a new heating and cooling system, which we're calling a hybrid system, that incorporates this thermal energy storage. And in order to kind of think about, well, how good is the system, we need to compare it to two distinct baselines. So one baseline we see in most commercial buildings, they use direct fire gas furnaces for heating and wet direct expansion coils for cooling. So direct expansion is really just the flow of a refrigerant through an air conditioner. So that's kind of this window AC unit you can kind of associate with direct expansion. Another baseline scenario is this all-electric scenario. So some of you have probably interacted with heat pumps. Our baseline all-electric scenario looks at air-to-air heat pumps. So this might be a wall-mounted unit that you'd see on the outside of a building, or perhaps a split system that you'd see at your home. Yeah, so we're comparing our new hybrid system to these two baselines. And in doing so, we also wanted to interact with stakeholders because, and I'm sure many of the folks on this call have experienced this, it's not great for us as scientists to develop solutions without actually talking to the people that use these technologies. That's, I don't know, we could get into how that's associated with colonialism and just problematic thinking. But anyway, in order to do this work, we wanted to talk to the people that are actually in these buildings that need this heating and cooling service. And so we looked at 3 different market segments. My team conducted over 120 interviews, and we talked to folks in large commercial retail stores like you see down here, folks that are using portable buildings. We see this a lot on school campuses, and also folks in the multifamily residential realm. So you can think of this as like apartment buildings. And each of these market segments has a different a different goal and something they'd like to accomplish in turning towards a more sustainable energy solution. So we see these commercial retail stores wanting to promote sustainable brands, portable building facility managers wanting something that's modular and easy to maintain, and folks that are living in multifamily residential complexes really hoping to lower their utility bills. Go ahead.
There was a question about whether Johanna Parton wanted to know, are there options other than lithium-based salts?
Yes, and actually the one that we're focused on a few different materials right now, but the primary one we're looking at has sodium acetate trihydrate, so it's a sodium-based salt. Hopefully that answers the question.
Carry on. Thank you.
All right, cool. So I'm going to briefly just touch on what these new hybrid, so again, storage integrated designs entail. So we have I'm going to go through a couple slides like this, a 3D representation of a building and how this new heating, ventilation, and air conditioning system would sort of fit with this building. So all of the systems that we've designed have an air-to-water heat pump. And so that's what you're seeing here. So an air-to-water heat pump basically uses air as a thermal reservoir and pulls heat or rejects heat to that air to condition water. And so this water then of the air-to-water heat pump is flowing through the rest of the system. And this water will be hot or cold. So this water can flow over to these hydronic air handling units. So maybe it's sending cold water over here, and this air from the building is passing over it and being cooled down. Or maybe it's sending cold water over to this PCM thermal energy storage, and it's freezing that thermal energy storage for later use. So air to water heat pumps can do both heating and cooling of this water. And so we see kind of in our technology solution for these large commercial retail stores that we're accomplishing that with this set of components. So our air to water heat pump, our phase change thermal storage at a cold temperature of 11 Celsius and a warm temperature of 43 Celsius. And then we also have one additional component in our large commercial retail stores, the sub-wet bulb evaporative cooler, which under appropriate climate conditions is able to provide cold water that we could use to serve building air conditioning needs or charge up our cold thermal storage. So I don't want to spend too much time on each of these, so I'll get into the next one. Our portable building system is actually very similar to what I just showed you for the large commercial retail stores. The main difference here is that these things are all packaged together in one, what we hope is a modular, easy to maintain system. So again, air to water heat pump, thermal storage, indirect evaporative cooling and heat recovery ventilation, which kind of improves the cooling or heating performance of our air handling system. And then the last market segment that we looked at, as I mentioned, was multifamily residential buildings. And here, one of the major energy uses in this building type is hot water. So water for your sinks and your showers and your dishwasher and laundry and all that. And so we are also looking at using a hot temperature PCM to provide storage and shift those thermal loads associated with hot water uses. And with all of this, we really need models at multiple scales in order to represent how we would integrate phase change thermal storage into this larger HVAC equipment. And so this maybe gets a little technical, but this is kind of what the modeling environment looks like. So this is physics-based, object-oriented modeling written in terms of a series of equations. And we have systems at different scales that are interacting with each other. So we have a building subsystem, which would kind of represent the loads, so the heating and cooling loads and also the hot water needs of the building. And this sort of also encapsulates the occupants and how they interact in that space. An air delivery system, which supplies that hot or cold air in order to condition the space. And then these hydronic plants associated with the air to water heat pump and our thermal energy storage or our evaporative cooling devices that are sending this hot and cold water to the air delivery subsystem, which is then conditioning the building. So this is the modeling environment. We're modeling all of our different system types using Modelica.
And Dre?
Yes.
Kayu's son asked, for multifamily buildings, do you mean the system provides simultaneous cooling and heating? For example, in the summer, space cooling and solar hot water?
So what we can do in the multifamily system is integrate a desuperheater. And this desuperheater, when the air to water heat pump is providing space cooling, can also kind of take the heat that would be rejected and use that to charge up thermal storage. So it's essentially using the thermal storage as a heat sink for the air cooling process. So yes, it could potentially provide simultaneous space cooling and water heating, but it also provides this capability that we can charge up these batteries and use them whenever they're needed. Does that make sense?
I'll let Kayu put that into the chat, but it makes sense to me.
Awesome.
Yes. Oh yeah, Kayu says, gotcha. Thanks.
All right, cool. Yeah, thanks for the questions. Y'all are better than my thermo students. Okay, so kind of thinking about those models, I'm going to just briefly touch on each of those subsystems. So first, thinking about that building subsystem, this has parametrized zones that actually match Department of Energy reference buildings. So the DOE has conducted these huge surveys in order to understand energy use in commercial buildings, and they've also done this for residential buildings. So we basically leverage that work to develop our building models. And so I kind of mentioned which building models these are based on here. And we use those design heating and cooling loads from this Department of Energy reference buildings to initially size our components, but then we end up resizing components based on simulations. We can actually put these systems really anywhere in the US, anywhere that we have weather data for a local meteorological year. And so this is available online. And then we've also modeled these water heating loads using the stochastic domestic hot water event generator. So I've put a few sources here, and I'll share these slides after in case anyone's curious.
One more question from Randall Higa of SoCal Edison. He asked, is the Coolerado system, the M to S cycle, an example of a SWEC, SWEC, or is it a different technology?
So I believe the Coolerado is an indirect evaporative cooler with heat recovery ventilation. So I think that's more like this device than it is like the SWEC. But it's possible I'm misspeaking.
And is there ventilation associated from Alice Sung? Like filtration, basically, filtration systems.
Associated with kind of these integrated systems that we've developed?
It might be a little off topic because you're talking about heat transfer, but one of the questions, because people are getting excited about it, is does it look like fresh air that's filtered?
Yes, so we would include filters, in these integrated systems. It's not something that we've explicitly modeled at this point, just because we have been focused on really capturing, those heat transfer transport processes. But yeah, the actual, kind of final technological product would definitely have air filtration, ventilation, here, like with the DOAS, bringing in fresh outside air for, to meet occupant needs.
Thank you.
No problem. Okay, so kind of thinking back about this modeling, thinking about these different subsystems, I'm just going to touch briefly on the air delivery subsystem. And so we're modeling the baseline, remember the gas heating and the direct expansion cooling, and we're modeling baseline all electric, which has that air-to-air heat pump, and our new system, the hybrid HVAC. And so we're actually able to kind of capture the differences between these baseline systems and our new systems in the way we represent the heating and cooling coils. And so I kind of just showed this here, no expectation to really read anything in this diagram. But the main point I want to highlight is that we can reuse and reconfigure these object-oriented models, which really cuts down time on our ability to run simulations and make predictions. And so we're really creating a tool that we're hoping people beyond the lab will be able to use one day. So yeah, hopefully this generates some excitement. I have a couple of details on the component models that are in these systems. So the heat pump model is sort of a simple COP model. And we're actually looking at field data. So there were kind of hundreds of heat pumps tested in the fields, and their coefficient of performance, or COP, was determined as a function of the temperature difference. So the source side temperature versus the load side temperature of these heat pumps. And so these data were compiled. And so this is the data that we're using to represent the performance of our heat pump in the model. And then looking at the thermal energy storage, which is another key component here. As I kind of sort of mentioned, but maybe not explicitly, we have 3 different phase transition temperatures, and those serve these 3 different purposes. So space cooling, we have our cold PCM; space heating, we have sort of a warm PCM; and then water heating, we have this hot PCM. And what you're actually seeing in the picture up here is our laboratory characterization of these thermal batteries, where we're running hot and cold water and measuring temperatures and using that to validate our models. So anyway, my goal, personal goal, is to, yes, validate these models and include these models in open source building libraries that other researchers will be able to use. And I know I'm running short on time, so I'll try to kind of wrap this up. All of this modeling fits into a parametric simulation tool that we've developed, where we can easily configure different scenarios. And by different scenarios, I mean, okay, what is the building type? Where is this building located? So what's its climate? What's the local electricity tariff or gas tariff? And all of this information gets put together and configured into a record, which is then compiled and simulated. And we produce these time series results, this time series data, where we can analyze the actual demand reduction that we've achieved and also any operating cost savings that we've achieved through load shifting. And so I'm going to kind of show just a sample result here. This is for the large commercial retail store, and we're looking at winter. So these are 3 days in winter. And this y-axis is the total building electric power. So we're going to be comparing the total building electric power for this baseline all-electric system versus our hybrid system. And a couple other things in this plot that are important to point out. With our hybrid system, because we have these thermal batteries, we have these different periods of operation. So we have blue showing when we're charging up the thermal battery, and pink showing when we're discharging it. And so what you can see here, kind of comparing the yellow curve with the purple curve, is that during those pink periods or those discharging periods, our electric demand, so this is our electric demand on the grid, is reduced compared to the baseline system. And this baseline system, you can see, has some sharp peaks. And anytime you see a sharp peak for an electric power profile, I want you to think about how that actually impacts the generation of that electricity. Because when we have peak demand on the grid, that actually means that our extra natural gas-fired power plants need to come online. And so reducing peak electric demand can really actually be synonymous with reducing greenhouse gas emissions. And so that's the ultimate goal here, is to shift this energy use to other times to kind of achieve more of a constant or regular flatter load profile in order to enable electrification of our power generation and our end use consumption. Any questions in the chat, Sean?
Yes. And first I'm going to go like, woo! That's
Thanks.
Brilliant. I loved how you brought it all home at the end, tied it back into GHGs. Good job. So Brittany Moffat asked, this is exciting work to see. Thank you for sharing. In terms of weather files for the simulations, did you or will you look at the future weather data, for example, weather shift?
I actually was not aware of weather shift, so I'll have to look that up. But yeah, we definitely need to, I mean, our climate is absolutely changing, and we need to consider the more extreme weather events, which are going to be part of this shifting climate. So yeah, we can input future scenarios into that kind of weather analysis as well.
And could you put your email address up? Maybe it's on your first slide as we transition over Andre. And
yes.
Folks that are have questions, could you put them into the chat? And Dre, could you work on answering them in there?
Absolutely, absolutely. And I'll share these slides with you as well. There's a little bit more info kind of in the next few slides if folks have additional things that they wanted to look at. And yeah, I'll definitely share my email and answer questions in the chat as well.